All right, guys. So we're gonna start differential equations today. Whenever you see differential equations, the actual method of solving them is easy. They're actually just integrals. Everything that you're gonna do in differential equations, the hardest part is gonna be the integral, because for one of them, you're basically gonna copy the formula from the cheat sheet, and then you're gonna be left solving an integral. So that's why if you're not really comfortable with integrals or something like that, I would take another look and see what I can do better. Now, for differential equations, what are they? Why do we need them? Why do we care about them? So differential equations. How many of you are doing economics? Just hands up. Okay. So I'm gonna try to give examples as far as I don't know if you've taken any micro, macro course or everything time-based, but there you would have something like, I don't know, K of t equals the capital at time t. Okay, let's assume you've seen this notation in macro, micro, whatever you want to consider. Then for those that are doing physics, you might have K being the number of particles or anything else. Now, the idea is this T is going to evolve. You know, you're going to have T1, period 1, 2, 3, etc., etc. Differential equation, the problem is that time isn't really separated into like really, especially when looking at the data, time isn't separated into so exact points. Like you can do per year, but if you've done the solid model, you know that the year method is not really good. So differential equations basically take care of the case where time is continuous. They basically don't tell you the change of something in a year. They tell you the continuous change, okay? That's why you need them. So I would just say, basically, they're just how you deal with any problem in continuous time. Now, the way I think of them is I start from the basic quadratic. This is how your quadratic looks like, the simplest version. And how does a quadratic look like? You just have a second degree here. In our case, differential equations, they look exactly the same, except you have derivative sign here. And now, the idea is that this x is a function of time, or this x is a function of time. So when you're solving a differential equation, you are basically just finding out the function that satisfies that differential equation. So for example, here in the quadratic, if I just said the a is 1, b is 2, and c is 3, x squared plus 2x plus 3 is equal to 0, and I'll tell you just solve it, assuming it's solvable. I think it is, but if I told you to solve it, then I'm expecting you guys to tell me x1 is equal to some number and x2 is equal to some number, right? When you're dealing with differential equations, and I would tell you the same thing, let's say I'm solving this differential equation, then what I'm expecting you to give me, I'm expecting you to give me x of t is equal to some function, okay? That's the difference. That's the difference, and that's what you're looking to do in a differential equation. You're looking to solve x. Now, the full definition of a differential equation is just, I guess, an equation for an unknown function that involves the derivative of that function. Okay, so the definition doesn't really help you at all. It's basically just what I told you. Whenever you see x and x prime, it's a differential equation. Now, differential equations are notoriously hard, and they can be even unsolvable in most of the cases. But for this class, we are going to be solving first order ordinary differential equations. I'll just write D since I don't have time. Okay. Now let me explain what each of the term means. First order. This is the highest order of the derivative, which you'll see. So if it's first order, it means you're not going to see x double prime, for example. Okay, you're not going to solve equations like that. You're only going to solve equations x prime. Okay. Now, and ordinary just means that your functions only depend on one variable. In most of the cases, and in general, and in most of 99% of the applications, it's just x of time. Your variable depends on time. And you're basically just the way you could interpret, I guess, this differential equation is the change in x across time plus 2x plus 3 is equal to 0. That would be, I guess, the interpretation. Obviously, when you're dealing with economics, you can interpret it in different ways, but I'm not doing economics right now. Now, just so we're clear, and I'm going to write it really clear because this is what you need to find out. X is your unknown function. And t is your variable. Right? Time varies. Now we're going to find for x prime of t. You'll find different notations. Most that I've seen is x dot, like this. But it's the same as just the derivative. Like, so, no, I mean, it's supposed to be just dx of t. If you're more familiar, if you're like writing it like this more, it doesn't matter, okay? It doesn't really matter. Now, I want, before we actually go on to teach you how to solve it, which is very, very short, let me differentiate between the type of solution. So you can have a particular solution which is some function that works for all t, just some function, emphasis on some, so it's some function. X of t that works for all t. And then we have the general solution, which basically is just the sets of all solutions. I'll show you what I mean in a second. Okay, so for example, x of t equals 24 times e to the power of t. This is a particular solution. I'm not going to write, but if you want, particular, or whatever. And then x of t is equal to a constant times et. This is the general solution. Right, like you see the difference. Basically, the second one includes the first one. Okay. I think right now you've not done phase diagrams, have you? No. Okay, cool. So we're just gonna go into solve. What does solving ODEs mean? Solving ordinary differential equations, ODEs, just so we become more efficient. So there are two cases. There are two cases which we're going to learn in this class. The first one is just going to be the linear case. And it goes like this: x dot plus x times a of t is equal to b of t. Okay? Everything of this type, I'm going to give you a method to solve. And then the other case which we're going to look at is the separable case, which just looks like x dot is equal to, let me not mess up the notation, f of t times g of x. And I will elaborate more on the second one when we get to it, but we're going to move on right now. And since we're here, I'm going to give you the three type of questions that you can get on ODEs. The first one is, so I don't know, type of questions. These are the three type of questions which, if you think you're comfortable solving, then you're good on differential equations. The first one is find the general solution. B is find a particular solution. I don't know what I wrote there. Particular solution. And the last one is what is a constant solution, which we'll get at some point. But ignore C for let's actually drop C for now. Let's actually drop C for now, since we're not there. Okay. So now let's like, this is basically all of ODEs. This, again, the solutions, the way to solve them is like very, very fast if you know integrals. So let's look at the linear differential equation. Linear differential. Okay, so just so we're writing it, the first part, which is always the most important, is identifying what your A of t and B of t is, which I highly recommend whenever you think it looks like this, whenever you don't have a product, just write it exactly in this spot. It's the same as the Lagrangian, where you were taught to always do maximization and always use a minus and always that sign. It's the same concept here. If you haven't done ODE differential equations before, I would highly recommend writing exactly the same spot. Now, the first step in solving this is computing the antiderivative or the primitive, or compute big A of t, which is the antiderivative of small a of t. Okay, that is the first step. And then you would just, well, I'll show you the proof for it, but again, you don't care about the proof. For all intents and purposes in this course, whenever you see this and you've computed big A of t, immediately use the formula and you're done. But maybe there's someone interested, I'm just going to show you the proof. So the whole idea is to multiply this equation by e to a of t. Okay? I know it looks ugly, but that's the idea. Now, you would get e a of t x dot plus a t x is equal to e a of t times b of t. And now the whole idea is that, well, you observe or you don't observe that this thing over here is just the derivative of e EAT times X with respect to T. And this is just EAT times B of T. Okay, so this is kind of the trick that this ugly thing is just this derivative. And now we just integrate both sides and I get EAT. Oh, let's write the integral nicely. Integral derivative with respect to D of T of EAT times X dt, very important, is equal to integral E A of T times B of T dt. And now you're basically almost done. Because this integral is by definition just EAT times X plus a constant is equal to this integral EAT BT dt. And now I'm just gonna write, like I'm gonna start a fresh page and write the formula. I'm just gonna multiply with this everywhere and get X. So the general formula for solving this is just X of T is equal to constant times E minus A of T plus E minus A of T times integral EAT B of T dt. And this is the only thing that's relevant, okay? Like if you wanted, I just showed you the proof for the people that were interested, but realistically, this is the formula that you are going to use. If you can't memorize it, no worries. It's in your appendix of like cheat sheet. You'll have it on your exam. So if you can't memorize it, that's perfectly fine. Although probably I would hope that you're going to do so many exercises that you will memorize it at some point. And that's kind of it. As I said, realistically, when you're solving linear differential equations, you got to solve one integral, two integrals. That's basically the whole problem. Okay, that's why I've called them undercover integrals. But let's just do an example. So the example that I'm going to write is this. This is the differential equation. So now, as I said, the first step is always bring it to the exact same version. So I know that I have to bring it to the version of x dot plus ATX is equal to B of T. This is what I have to bring it to. So I'm gonna make it look as similar as possible. So what am I gonna do? I'm gonna move 2x on the other side, and I get x dot minus 2x is equal to 1. Almost exactly the same, but I said that we need exactly. So plus minus 2x is equal to 1. Okay, now it looks exactly the same. The next step that I'm going to do is I'm just going to identify the stuff. Okay, so if you look here, then I can just write that A of T is equal to minus 2 and B of T is equal to 1. All right, what's the next step that I said? The next step I said is we have to compute A of T, which is the integral of small a of T dt. This is just the integral of minus 2 dt, which is just minus 2t. Now, I'm not going to write a constant. You don't, when you're computing this, you don't have to write a constant. Okay? No constant here. Yes?
Why is it not minus?
Excuse me?
Like when you take the 2x over.
Oh, completely true. Yeah. No. I missed it. Yeah, minus 1. Completely right. Yeah. It's minus 1. I don't know where my minus left. Yeah, so now it's correct. Now if you identify correctly, we're good. And now you don't need to do anything else. Once you've done this, we just plug in the formula. Can I zoom out? Maybe no, I can't zoom anymore. So I just plug in the formula. X of t is equal to a constant times e to minus at. So in my case, it's minus 2t plus e to the minus 2t integral of e to minus 2t bt, that's minus 1 d of t. Okay, so I immediately just slapped the formula. I just replaced, just so we're clear, this is a of t, this is a of t, a of t, b t. All right, and now I only have this integral left to solve, which I think at this point we should be quite comfortable in solving. This is just e to the power of 2t plus e to the power of 2t. And this is just e the minus 2t over 2. Yeah, that's fine. Again, there's no need to write the constant here if I remember this one here. They're just going to cancel out. You can try it for yourself or you can believe me. Both of them work for me. So now my final answer is just x of t is equal to constant times e to t plus this cancels out a half. And this is my final solution. I'm done. Any questions on what I did? Yeah.
Yeah, why don't you need the solvation?
Because if I wrote a constant here, it would be plus e times 2t times d, right? D being the constant. Or like, it would be plus d like this, okay? Where d is a constant. And the idea is that when I open the parentheses, this e to the power of 2t times d, I have c plus e to the power of 2t here. So I'll just have e to the power of 2t times a sum of constants. That's why I don't need to put it there. Yeah.
Could you go back to the last page and just go through what AFT and DFT are again, and like what we're trying to find?
Here?
No, the last page.
This one?
Yes, and just the beginning again, like what were we trying to do?
So the first step when you see a linear differential equation is recognizing it's a linear differential equation, so it's with sums. Then the next step is to identify what is A of t and B of t, like pinpoint what they are. Then you just have to compute A of t, which is the antiderivative of small a. So basically just big A of t is just integral of A of t dt. You just got to compute that. And after you've computed this, you skip all of this and you just plug it in the formula. That's all really. So just looking at my example, I had this example over here, and I remember that this was my linear differential equation. So my first step was to bring the problem that they gave me to the closest form to the linear differential equation that I can. So I just moved this on the other side, and I wrote it, instead of minus 2x, I wrote plus minus 2 times x. This way I can just highlight that this thing is A of t, and this thing is B of t. Once I've done that, I need to compute the integral of small a. So I am computing the integral of small a. And I get that A of t, big A of t, is equal to minus 2t after computing the integral. Now that I've done that, I'm basically just gonna use the formula, and I'm gonna replace my things in the formula. And that's it. So does that answer?
Yes.
Okay, cool. Now, how do you check if we did it correctly? You don't have to check unless you want to or the problem asks you to, but how would we check? So my solution is x of t is equal to a constant times e to the power of 2t plus a half. And my equation was x dot is equal to 2x minus 1. How do we check this? Well, remember when I said that x dot is basically just the derivative of x. So it's just derivative of x of t with respect to t, which is just derivative of, I replace constant e to t plus a half over d of t, which is just going to give me 2 times a constant times e to t. Okay? So just compute x dot. And now what's my last step? I'm just going to plug in here in my equations and see if it works. So x dot is this. So I have 2 times c times e to the power of 2t is equal to 2. My x, I plug in the x from here. So it's 2 constant e to t plus a half minus 1. Open the parentheses, 2 times a constant e to t plus 1 minus 1. It works out. So my solution is correct. Okay? Never forget the fact that this x dot or whatever is just the derivative. I don't know if that might come in handy, but I've seen some tricks in like the 0.01 cases where you actually skip the whole solving of the problem. Okay, now let's try and see if we can get a nastier problem. Okay, let's build on this one first. One problem, so they might not ask us to solve this equation. They might just tell us, take this equation x dot equals to 2x minus 1 and find, then they're just going to say, find particular solution of x such that x of 1 is equal to 2023. Okay? They might just use this phrasing over here. So they're asking for a particular solution of x such that x of 1 is equal to 2023. What do we do? So when you're dealing with this sort of problem, the answer is you solve for the general case. So you do everything we've done before. So the method is solve for the general case. And we're going to get the same exact thing because it's the same differential equation. So let's write it here. C e to the power of 2t plus a half. Okay, so we solve for the general case and we get this general case. And what do we do now is we just plug in these numbers. Okay, let me explain. So x of 1 is equal to 2023. It means that t is equal to 1. And since I know x of t, I'm just recopying my solution so it's on this page. So all that I'm going to do is I'm going to make this equal to 2023 and plug t equals 1. And what am I solving for? That's the key. You're always solving for the constant. Okay, so here's what's going to happen. If I just do exactly what I said, I'm going to have constant times e to the power of 2 times 1 plus a half is equal to 2023. So my constant is just 23 minus a half over e to the power of 2. So, and now I basically just write x of t is equal to 23 minus a half. I replace my constant with this, and I copy everything else. And this is the particular solution that they were asking for. Okay? So, in terms of methods and what you actually have to do for particular solutions, it's just solve the general case. So, and you get the general formula. And then you just plug in what they're telling you. So you plug in t equals to what they tell you, and x equals to what they tell you, and you solve for the constant. That's the most important part. You got to solve for the constant. I even wrote it, and that should be kind of intuitive, because when I first introduced general / particular solutions right here, I gave you the exact example. The particular solution is the same thing, just that the constant has a number instead of c. Okay? And the idea is that that number, in our case, just works magically. If I would plug t equals 1 here, I would just get 23. Okay? That's the whole idea of particular solution. So if there aren't any questions, I guess we could do a more difficult one. This is actually quite lengthy, I think, in proof. But let's see. So I'm gonna do you a favor, since I am I'm gonna write it for you in the nice form. Okay? Just because I'm a nice person, I'm gonna give you the nice form. Now, because it's kind of get ugly. 1 second. All right, because I'm even nice. No, it's fine. We'll leave it like this. We can't be that nice. All right. So this is what we're gonna solve. Obviously, it's a little bit uglier than before, right? Why? Because if we write the x dot plus a t x is equal to b of t, the functions are much uglier, right? Like in the previous case, I had these functions being equal to constants, which makes integrals very easy. But in this case, it looks kind of bad. So let's see what's the time like. So I'm gonna help you solve. I'm gonna help you set up your problem, and then I'm gonna give you 5 minutes till the break to think about it on how to solve the last part of the integral, because I think it's quite interesting. So again, same method. I write my differential equation to the same way that I've learned, basically. And in this case, the professor was nice and he gave me the exact same form, so my identification was simple. So I identify AT equals this, BT equals this. My next step, pretty standard, I just compute big A of t integral A of t dt. This is nice as well, right? Because this is just integral of 2t dt. This is just t squared. Again, I could write a constant, but I told you it's gonna go away, so don't need to bother. T squared. This looks good up to this point. Now, I'm just gonna use the formula, and I'm gonna write x of t is equal to a constant times e minus t squared plus e minus t squared integral of ET squared T to the third. This looks bad. D of T. Okay? So this B of T. This big A of T minus big A of T minus big A of T. All right. Now we're so everything to this point, I think it was easy, right? Now comes the hard part. How do we solve that integral? And I'm gonna okay, any ideas before I'm giving you a hint? Any ideas on how we could solve that integral? Just looking at it. Anything. Hint, yes, you technically know everything to solve this one. And there are no very hidden tricks. There's nothing, I think we even solved it in some case, but in another form. There's no hidden trick on it. It's quite clear. So what helps you in this class is the fact that realistically, you don't know that many methods. They're not like 20 methods which you have to check which one to apply. You know 2 of them, right? You know substitution and you know by parts. So if you were to attempt to try the by parts on this, what would happen? I don't know. Let's try. Let's try. Since nobody's saying anything, we're just gonna try. And I'm gonna write in parentheses, attempt. Because realistically, I don't think there's double T's there, but whatever. We scratch that. Let's write it simple. Try. Because once you reach a certain level in math and it's kind of becomes hard, you just gotta try. You try different methods until you succeed, and that's kind of the way to go. So in my case, I don't know if this is first case, f prime of t is equal to et squared. G of t is equal to t to the third. So g prime of t is equal to 3t squared. Integral of et squared d of t. This looks horrible. And I think realistically it's actually unsolvable. The second one is I take f of t being et squared, and g of t is equal to t to the third, t derivative. So integral, g of t is equal to integral t to the third dt. This is t to the 4th over 4. This f prime of t is equal to take a derivative, and I get 2t times et squared. So now we get to the point where we wrote the 2 cases of the by parts, and we think which one is easier to work with. In this case, it's not really a solution because because this you can't solve. So I would have to use this one. And the problem with using this one is that my powers are going up. I'm getting another t here, I'm getting a t to the 4th here, so it's getting worse and worse. Remember my whole argument when I said that if you're going from bigger powers to smaller powers, you are doing well. If you're going the other way around, you're not going to solve it. In this case, I'm not going to solve it. So what did we learn from this method? Not working. Okay? And until you kind of get the sense of what works and what doesn't, you just got to try. So now, if you get to solve this problem in your class, it means that you can solve it. There must be a way with what you know that to solve it. So I only have one more trick, which is substitution. Last resort. If this doesn't work, then the only solution is panic or report the professor. So let's hope this works. What substitution am I thinking of? What should I use? Well, kind of hard really, but what I would say is a good substitution is t squared is equal to u. That was my idea. There's some other ideas which you can do, but it requires a little bit, it requires it to be very tricky with computation, which I would not suggest. So now let's just do what we learned, right? So take a derivative d of t times the derivative of t squared derivative of t is equal to du. dt times 2t is equal to du. All right, now let's see where we're at. Integral et squared t to the third dt is equal to integral e, instead of t squared, I can write u. E of u times, now we panic. We have t to the third dt. We're panicked. Okay. Now now we just need to observe that this t to the third is just t squared times t. Right? Why is this observation very good? Because this is u, and because this is du from here. Make sense? Everyone's seeing it? So my claim is that this t to the third and dt are pretty bad. So I can just write it as integral of u times t squared times t times d of t. This is t to the third. Right? The same equation as before. And now I can just group my stuff up. So this is du. And this is just u. Any questions? Yeah.
That's two.
Oh, sorry, there's a 2 somewhere. Where is it? Where's my 2? Yeah, oh, sorry, I can, yeah, of course. I can just create, okay. There's, yeah. So there's another trick, which you do 2 times a half. Okay, great catch. So you create your du like this. Sorry, I missed it too. Okay. So you have this du over here. And now your equation basically just becomes a half, which I forgot, a half times integral of eu times u du. So again, in case the substitution wasn't clear, I'll write it one last time here and then we take break. So I chose t squared is equal to u, and then I computed what dt is in terms of du. Once I've done that, I go back to my original equation and see what I can replace. I can replace the t squared from above with a u. Right? That's the whole reason I changed stuff. I can replace that, and now my equation is just integral e to the power of u times t to the third dt. Once I have this equation, I want to replace more, so I'm going to write e to the u times t squared times t dt. And now I can, just so we're clear, this is t to the third, like that's what's happening. This t squared becomes u, and this t dt from my equation up top here, however you want to write it, is just t times dt is just du over 2, however you want to write it. But this is just du over 2. And that's how I get this equation over here, which is a classic example of solving it with the by parts method, which we're gonna do afterwards. But I think we could take a 10-15 minute break right now, and yeah, come back after. Okay, now that the crisis has been averted and I have an iPhone charger, we can continue with our work here. So any questions on the substitution that I did here? Or is it kind of clear? You know, hard to see, but clear what I did. No, hindsight makes sense. Now we just have to solve this one, which is just by parts, right? Like this is one of the cases that I've said from the start. When you see exponential times a power, it's a clear by parts method. So I'm just going to apply by parts to this. So a half, I'm going to still write the step, but I promise this is the last time. So again, the first case, f prime of u, whatever, or f prime is equal to e of u. And then g of, okay, that's right. G of u is equal to u, so g prime of u is equal to 1. F is equal to integral e of u du, which is just e of u. And then the second case is when I take f of u is equal to e to the power of u. And then g prime of u is equal to u. So g of u is equal to integral u du. That's u squared over 2. And this is just e to the power of u. Now again, we spend a second to look and compare the two cases, e of u, so that doesn't change, but there's a constant here, there's a ugly formula here, so it's kind of clear that we're just going to choose the first one. Okay, always choose the easiest one, or let me rephrase it nicely. The easiest one is always a prime candidate to be the solution. Okay, you can quote me on that, but I'm just going to use this one, and I'm going to say, I'm going to put the 1/2 in the end. Integral EU times U du. So this is f prime, this is g. So I got to add plus integral f is still EU, g prime is 1. The u is equal to EU times u. So it all kind of looks nice. EU times u minus e of u plus a constant. All right, pretty standard. Now, am I done? Well, almost. First of all, is don't forget the half from here. So I'm gonna drop it down here. A half, a half, a half. First step. Now, second step. The second step is probably just remembering why we started to compute this ugly thing in the first place. And the reason, and we were at our differential equation, which I don't have my pages anymore, but I will try to write from memory, was something like x of t is equal to e to t minus t squared plus times a constant plus e minus t squared times the integral of e t squared t to the third d of t, right? Like I think this was the original equation we had, and we finally managed to solve this one. So congratulations to us. So now x of t is equal to e minus t squared times a constant plus e minus t squared 1/2 e to the power of u times u minus a half e to the power of u. Now, am I done? The answer is no, because I mentioned that when you're dealing with substitution and you don't have limits of integration, you can't have banana and apples combined, right? So if I have t here, I need to have everything in with respect to t here. So I'm just gonna replace u with t squared for my original substitution. That's the last step. So my final answer is just gonna be x of t is equal to e minus t squared times a constant plus e minus t squared, a half e t squared times t squared minus a half e t squared. And if the problem only asks you to solve, then you can just leave it like this. Can you make it look nicer? Sure. Do I care to make it look nicer? Not for now, at least. For now, no. So if they just ask you to solve this, you're done. Okay? As you can see, differential equations or basic integrals at this point just can get very complicated, right? But the theory, the actual theory of how we got here, how we got to the answer was quite short, right? The only thing we had to compute from our original differential equation, which was x dot plus 2t x is equal to t to the third, our original thing, all that required us to know differential equations, all the theory behind differential equations just told us that this is a of t, this is b of t. We computed big A of t, which is integral of small a of t dt, which was just t squared, and then we plugged in the formula, and then we were stuck with solving an ugly integral, right? So all that I'm trying to say is that the hard part about differential equations is not the formulas, and I would hope at this point is not the identification here either. The hard part about them is actually the integral that's hidden inside. Okay, and yeah, now let's assume that part A, this was part A, they were asking us for the general solution. Now assume part B asks us again, out of lack of originality, I'm just going to assume x of 1 is equal 2023. Let's actually just make it a little bit easier for myself. X of 0 is 2023. Okay, they are asking for this particular solution. And I've already done the first couple of steps, which was solving the general solution. This was my general solution. So now I'm just going to plug in the values. I'm going to say t equals 0 and x equals 2023. Plug in and let's see what we get. So x of 0 is equal to e to minus 0 squared times a constant plus e minus 0 squared, 1/2 e 0 squared, 0 minus a half e 0 squared. What a great decision I made with this 0. Everything looks nice. So 0 squared, 0 is, this is just 0, this is just 1, this is just 1, this is 0. Oops, so I'm just stuck with x of 0 is equal to a constant minus a half from here, and I need this to be equal to 2023, right? Because x is equal to 2023, so constant is equal to 2023 plus a half. And that's it. So again, realistically, the only hard part of differential equations are the associated integrals. Any questions on the actual differential equations? Otherwise, I'm going to give you like an actual. Is this simple actually? Let's see if I can cook up a quite simple one. Sure, let's do it this way. I'll give you 5 minutes for this one. x dot is equal, wait, give me a second. I gotta create something special for you guys. E minus x minus 2x dot is equal to um 4. Is 4 a good number? Yeah, it should be fine. Yep, looks fine to me. 4x. That's fine. All right. That's fine. All right, guys. Let's see where we're at. So, first of all, you were all kind of working, so I didn't want to mention that there's a chance it might not be solvable, because I'm just, it's too early in the morning, so I'm just still getting up. But, let's see what we can do. So our general was something like x dot plus at times x is equal to b of t, right? So this was our general, and I said most important, before you start your work, just try to make it look exactly the same. So my first idea is I'm going to move this on the other side, and I get 2x dot plus 4x is equal to t. And now what I'm going to do is I'm just going to divide by 2. And I get x dot plus 4 divided by 2, that's 2x, equals a half t. Okay, now it looks as close as possible. So identifying a of t is equal to 2, b of t is equal to a half t. Looks pretty nice to me. So let's see. First step is I have to compute big A of t, which is just integral of at, which is just 2t. That's actually pretty good. And now I just plug in the formula, and I get x of t is equal to constant times e minus 2t plus e minus 2t, integral of e to t times b, which is half of t dt. All right. And now we are, hopefully, I would assume that this thing looks kind of familiar to you guys right now. It's just made basically the 6th time we're solving it. But let's solve that one. So I have integral of e to t, a half t dt. I'm just gonna say I'm moving this thing in front. And now, yeah, I'm gonna rewrite it just so it's looking back at you. It's this e to the power of 2t, which is a classic by parts method, right? Like we've done it a couple of times by now. Since, yeah, let's obviously, by now it should be automatic that you want to take a derivative of this just so it goes away. So I'm just gonna say that let's f of t is equal to f prime of t is equal to t to the e to the power of 2t. So f of t is just integral e to t dt, which is just e to the power of 2t over 2. G of t is equal to t, so g prime of t is equal to 1. This was my whole idea, so I'm just doing it like this. Applying the by parts. Integral e to t times t dt is equal to plus. All right, let's do it with plus. Is equal to plus integral e to t over 2 times 1 dt is equal to t times e to t over 2. And I think we did it correctly, hopefully. Why is it kind of nice right now? Is because I have e to t times t dt, plus this integral over here is just e to t over 4 is equal to t, plus a constant is equal to t e to t over 2. Move everything to the other side, and I get e to t times t dt is equal to t times e to t over 2 minus e to t over 4 plus a constant. I know I could have written minus, but as you know, it doesn't matter really what I put there. All right. So now that I solved this, we're going back to my formula, which is x of t is equal to c minus 2t plus e minus 2t times a half times this integral t dt, and I've just computed up top, so I'm just going to replace, and I am officially done. Cool. This was it. Any questions on what I did? I think outside of basically just computing this integral, which at this point you should have seen it quite a couple of times, I didn't do anything special. All right. So if there are questions, I would probably just introduce the separable today, and maybe see if we have questions tomorrow, or see how he goes out there. But separable differential equations, you should, from the name, it means that you can just separate them, right? So they look like this: x dot, so the derivative is just equal to f of t times g of x. What's the idea? The idea is that this thing only depends on x, no t, and this thing only depends on t, no x. You got it, separable, they can be separated from the name. So that's the whole idea. They can just write it as two terms where one of them is only depends on t, one of them only on x. Examples are something like x dot is equal to e to the power of t times e to the power of x, or x dot is equal to e to the power of t x squared minus 1. Right? Like this thing only depends on x, this thing only depends on t. Now, we're going to have what's called a constant solution in this case. So this only is for the separable constant solution. The idea is, let's actually take this example over here. Let me ask you this: if x is a constant, what's the left side of the equation? What's x dot? If x is a constant, if x is 5, what's x dot? Yes, exactly. So if the solution is constant, it means this is 0. Now, you can't, since t is time and it flows and it doesn't care about you, you can't say that that is 0. So what you do when you're looking for constant solutions, you just say, this is g of x, this is f of t. When you're looking for constant solutions, the whole idea is to look for x's such that g of x is equal to 0. What's the idea? In this case, if I just solve it, if x is equal to plus minus 1, then g of x is going to be equal to 0. And x dot is going to be equal to 0 because it's a constant. So these x's, x equals plus minus 1, solve this differential equation. They are a constant solution to it. Okay. Obviously, this isn't the hard part of the thing, but it's always really important to start with the constant solution. Whenever you're solving separable ODEs, the first step should be identifying the constant solutions. First of all, because they might be what the problem asks you to do. And second of all, is because it's crucial for how we're actually solving them. Well, let me show you. Let me write it as a title, actually. How to solve them. So the method is quite related to the name, right? How to solve them. They're separable equations. So my first idea was just separate them. I know it's not a great idea, but it's all I can do. So I'm just going to divide by g of x, the equation. And now I hope you understand why we need to check the constant solutions, because I can't divide by 0, right? If x is equal to 1 or minus 1, then g of x is equal to 0, and I'm basically dividing by 0, which means that all that I'm doing is 0 points, okay? So always check, the reason, and I'm going to write it, the reason I can divide is because I checked g of x is equal to 0. Okay, so it's quite important in this case. Yeah. Now I'm gonna get x dot over g of x is equal to f of t. All right, this doesn't really look like much, but and now there's not much. There's not the only theory that's remaining here is that if I integrate both, so I integrate x dot g of x d of t integral f of sorry about it. I'm sorry, I'm a little bit okay. Let me write it in steps. What's x dot? So x dot is the derivative, okay? This is just d of x over d of t. So let's just write it like that. So maybe it's clear why I do what I'm doing. Okay, this is the equation, and now I multiply by d of t on each side, and I get dx over gx is equal to f of t dt. Now if I integrate both of them, this is just integral of 1 gx dx is equal to integral f of t dt. And this is where all the theory ends. There's no more theory after this. Now you just got to solve two integrals, the left-hand side and the right-hand side. So literally the theory says that you will solve these and you will get some hx from here, from the first one, equals to big F of t from the second one, and you're going to add a constant, and that's all the theory. So it's basically just h prime of x is equal to integral of 1 gx dx, and f of t is equal to integral f of t dt. This is all the theory. So basically, when you're dealing with separable equations or separable differential equations, after you check the constant solution, you got to solve this. This, I'll even write here. This is important. Like, this is something you should remember. Now, when you're presenting the solutions for a separable, when you're presenting the solutions for the separable, you first have the constant solutions. Like they are a solution as well, so don't get it wrong. And B, you just this is gonna give you sorry, not this one. This one from here is gonna give you a general solution. That's kind of how it goes. All right, let's see what we can do. Let's take an example and see how it works in practice. So since I'm here and I'm not really good with the small computation, let's take a simple one for myself, and then you're gonna do a one for you guys, more challenging. So x dot is equal to 3x. I can't really make it simpler than this. So what do we have here? We have x dot is equal to f of t times g of x. Again, really important is to bring it to the same form you know, and then identify. So I'm identifying right now. I'm just saying this is g of x, this is f of t. All right, so f of t is equal to 3, g of x is equal to x. Now, one important thing that I can tell you right now is if your identification here is correct in the sense that there are no x's here in f of t and there are no t's in g of x, then you're good. So for example, in this case, I could have just said that, you know what, this thing is g of x and f of t is equal to 1. Okay? So this identification is correct as well. The only important thing when you're identifying, and you should immediately sense that something's bad, is if I had something like f of t is equal to 3x. If that happened, that would be terrible. Okay, and it's gonna happen several times. So always when you identify, if you split it, I don't care how you split it, the numbers don't matter to me as long as there's no x in f of t and no t in g of x. It kind of seems reasonable, I think. So but yeah, just pay attention to that. Well, now that I have my things, f of t is equal to 3 and g of x is equal to x, I'm just going to apply the formula, which says integral of 1 over g of x dx is equal to integral f of t dt, right? Any comments? Well, I said first we gotta look for the constant solution. So this is bad. Like I don't write this. I say constant solution. G of x is equal to 0, which implies x is equal to 0 is a solution. Okay? I found a solution. G of x is equal to x, just in case you forgot. Okay? Now I can, and only now I can move to the general case. And I write integral of 1 over gx dx is equal to integral f of t dt. Right, so the first time I wrote it, it wasn't wrong, just the timing of it was wrong. Like the formula itself was correct, the timing was wrong. Now, we're just going to replace this g of x is x, this f of t is 3, so I get integral 1 over x dx is equal to integral of 3 dt. This thing is ln absolute value of x is equal to 3t plus a constant. And now, let's put, so what I wrote here with absolute value is completely correct, but I know some of you are really not familiar with it. So just so you don't focus on this, I'm just gonna, and I don't get yelled at, I'm just gonna say x is greater than 0. Okay. Just so we don't get stressed about that. So ln of x is 3t plus a constant. So x is just equal to e to the 3t plus a constant, which is equal to e 3t times e to the constant. Careful, when you're raising to the power, x is not equal to e 3t plus e to the constant. This is very bad. Like, it's not bad, it's very bad. Okay? This is the correct answer. And now you can just write it nicely as just e 3t times a constant. So this is the general solution. Looks pretty nice, right? And yeah, this is kind of all there is about this separable case. Obviously, I think the identification in some problem might be a little bit more challenging, in the sense that, let me see if I can create one that looks very ugly. I can just write it as x plus 3 ln of x is equal to t plus times x to the 3 times I can't actually create one unless it's gonna be too ugly. But what I'm gonna say again is what I've seen the most mess ups in this problem is literally in the identification. Like, it's so obvious, but if you don't write the identification correctly, there's no way we're gonna solve the problem. So always try to identify and don't rush in the problem, because let me put it in a nice way. If you rush in a problem with a wrong identification versus you just write the formula here, which we all know, you're going to get the same amount of points. Really, if you write one line or 10 pages with the wrong identification, you're still getting 1 out of 10 or 2 out of 10. So identification is very important. And then computing the integrals is, again, quite important in this case. Specifically, I'm emphasizing this problem over here, ln of x, this one over here, because as you probably guessed by now, or you should probably see it, integral of 1 gx dx, if you've had some experience with integrals, is more or less usually, 90% of the cases going to give you ln of something. Okay? I'm just going to tell you right now that this, on all well-behaved functions or something, usually gives you ln of something. And the problem is that people write ln of x is equal to 3 times plus c, and then they say x is equal to e3t plus ec. So x of t is equal to e3t plus a constant, versus what I wrote up top, and I got xt is equal to e3t times a constant. So first of all, in case it's not obvious why they're different, and you might ask, and you might say, we just don't care about this. Let me give you an example where it actually matters, and you're gonna lose literally everything. So these are your general equations. We're gonna do your version versus my version. And I'm gonna say find particular solution, x of 1 is equal to e to the power of 3. Okay? So we do the same exact thing. And let's split the page in two. In your case, x of t, e3t plus a constant. X of 1 is just equal to e to the power of 3 plus a constant. And I need this to be e to the power of 3. So constant is just equal to 0. In my case, x of t is equal to e3t times a constant. So x of 1 is equal to e to the power of 3 plus times constant is equal to e to the power of 3. So constant is just 1. So as you see, we just got different results. And I'm gonna be honest with you. In this, like, if you solve everything correctly here, and you wrote this at the end instead of this, I'd probably give you 9 or 8 out of 10. Realistic. So you're not missing much, right? It happens. On the other hand, if the next problem is find a particular solution and you do this instead of you do the left hand side instead of the right hand side, I'd probably give you 1 out of 10 because realistically you didn't solve anything that I was asking for. Okay, so huge impact, especially since I've seen in this class that the majority of problems are building on each other. Like we have A, B, C, D, E, F, G. Imagine there's another C right now, which asks you to prove something about this constant. At that point, you're basically kind of, I'm not going to say something rude, but you're definitely messed up because you're losing the whole problem. So yeah, that's kind of it. Unless you have any questions, you're kind of free. We're going to do some more examples on the separable tomorrow. Hopefully a little bit more challenging. And yeah, that was all for today.